Okay, then hello once more for you and for everybody who will watch this recording at home. Then what we finished on? We finished on the last topic about direct current. Yeah. About such called Thevenin theorem or equivalent generation method. Generally, everything that we have, it is some blocks for building of mathematical models, some simple ideas, and then when we take some task, take some challenge on the real object, we just combinating these ideas into the whole model for engineering calculation. That is why we are looking on some simple practical examples, but the most important thing just to understand and remember these main blocks, these main approaches of mathematical apparatus. Then we have combinations, equivalent transformation of resistors, how to transform resistors inside some model, inside some circle. Also, we have mesh current method and node voltage method. In first, we making substitution of unknown variables for searching some imaginary current that we called mesh, and it is more simple way for calculating. In the second approach, we are using voltages, the potential of some nodes, and both of these methods, they are transformation of the general physical laws as Kirchhoff's law. Just transformation of these main laws. Also, we add to them superposition theorem, as it could be said that method number 3, but generally first two are used when we want to calculate everything, all currents, all voltages, all powers inside system. But superposition theorem, mostly it is additional method for or divide different type of signals into different calculations, or transform something complex into some simple parts. For example, if we have non-sinusoidal signal, we could transform it into the couple of sinusoids, or if we have such called non-symmetric system, it means that consumers are quite different. We could transform them as a superposition of some symmetrical systems, and so on and so on. If we have a couple of different sources, for example, a DC and AC source that operates simultaneously, we could divide them into different calculations. That is why generally using this method, we could find everything. We could find all currents, all voltages, and all powers. But generally, it's used for some transformation of our calculational direction, just to represent something complex into couple simple parts as a superposition of these simple parts. And the last one is such called equivalent generation method. It is also representation of complex system in more simple way. And as we speak previously, the idea was we represent any circle with sources and consumers as a simple part with 2 points of connections. And inside this simple part, we have one equivalent source or voltage or current as it more comfortable for us, and a resistor. It could be inside or voltage or current source, which is better for our calculation, and resistor. And such transformation is quite useful when we interested in one single branch with one single consumer. Not to find everything as here, but for example, if we have repeatable calculation of some different consumers inside single branch. For example, 100 different consumers, and it is only one point, only one element that is changed in our system. That is why it isn't it isn't efficient to calculate each time everything inside our circle. It's much more efficient to calculate only point of our interest, only some part of system which we are interested in, and that is why to substitute all other parts of the system that we aren't interested in as an equivalent generator. It was the idea. And that's all for for DC. Then also today we will discuss the alternating current, sinusoidal current, and we also could use all for this method into the sinusoidal current, and also could use transformation of resistors into the sinusoidal current. Everything will stay valid with some transformation, with some, I think, it could be said with some transformation, but generally everything stays the same. But in AC, two other elements will be added to our model as coil for magnetic field and capacitor for electric field. Not only consumption, not only transformation of electricity into other types of energy, for example, heating, light, mechanical work, because resistor, it answers on all these questions. It models a transformation of electricity into other type of energy. But coil and capacitor will model transformation energy inside our electrical circle without consumption. For example, from magnetic field to electric field, from electric field to magnetic field, but without consumption, without decreasing amount of energy. But it will be a little bit later. Then last couple words about equivalent generator. Last time we finished to discuss about energy transmitting. And after that, we'll move to sinusoidal current. Yeah. Couple examples that we did last time, that instead of some circle with lots of elements, we substituting equivalent generator only as two elements. Here we substituting 4 elements as 2, but in the same way we could substitute 400 or 4000 elements as single 2. That is why that method is quite comfortable if we are interested only in the right part of circle, in some specific branch, specific consumer. Then, what we finished last time about, where it is, okay, without specific marker, but about power maximum. Okay, just speaking about power transfer, the equivalent generator method is quite useful to discover properties of system in terms of power transfer. What does it mean? It means if we have some circle, and generally divide it into source and consumer. The left will be source with internal resistance R, and the right one will be consumer. Then, if we are varying resistivity, if we are varying consumer, increasing the resistivity, then we are increasing the total resistivity of this whole circle, because the total resistivity equals summarizing of them resistance of Thevenin source. The serial connection is called Thevenin. The parallel connection with current source is called Norton, just by the name of scientists. But for this Thevenin circle of two elements, internal resistance plus resistance of consumer as a variable also will increase. That is why the current will decrease. The current in this circle will decrease as we see it. And also voltage on the consumer could change into some way as we look on the voltage here, or let's make the same color because the same consumer. Voltage will also change. Voltage is a multiplication of current and resistivity. And we have situation that current decrease, resistivity increase. And voltage will be depending which process is more quicker. If resistivity increase higher, quicker than current decrease, we will obtain increasing of voltage. If our resistivity increase slower than current decrease, we will obtain decreasing of voltage. It just depends on the curvature of our function, which curve is more curve, which curve have the bigger derivative. That is why, as we look on the voltage, we see that it always increase, yes, if I'm not mistaken. It is some experiment for measurements, because that is mean that resistivity increase much quicker than current decrease. Okay, no problem. Then voltage increase. Then the most interesting thing about power, because as we look on the power, it increases, obtains some maximum value, and then also decrease. It has some specific maximum. And this dependence could be observed on any type of system which transports electricity from source to consumer. We always will obtain some power curve with some maximum point. And the areas of small power and areas of high power. Why is it so? Because power is a multiplication of voltage and current, and the same idea that I speak about voltage. Which function changes quicker, current decrease or voltage increase? Here are the graphs. Decreasing of current, increasing in voltage, and power as multiplication of these two functions, depending on the derivative, in which point derivative of each function is higher. How this graph, this blue graph for power, could be obtained mathematically? How could we find the maximum point here? As we find in extremum for any function, the maximum point could be found as function derivative per some parameter. As if we build in on resistivity, we could take derivative or by resistivity or derivative by current if we are building power dependence from current, and equalizing this derivative to 0. This equation will give us maximum point, because in maximum point the derivative or tangent line will be parallel to x, and because the angle of this tangent line equals 0, then the derivative should equals 0 in this point. Because in any other point, tangent line will have some angle. Angle between x horizontal x. Then let's check it mathematically for this circle. Just calculate the power. Let's look on the same picture. Power of consumer equals I square R, joule heating. Then current, the total current, equals voltage divided on total resistivity on both resistors. Then power should be E square, summarizing of resistivities in square, and multiply on R load. Then the derivative of this value should equals 0. We are taking derivative per R load from this equation. We have multiplication of two parts depending on the R load. That is why we are using a formula equation of derivative from multiplication. It will be a derivative of, or even we could take formula derivative of dividing, because we could write it as E square R load, and in bottom part will be R of our generator plus R load in square. And we will use formula of derivative of the ratio. It will be E square on bottom part. There it will be derivative. Sorry, I will take the other color. Derivative of ratio, it will be derivative of upper part. From E square R, it will be just E square. On the bottom part, multiplication on bottom part, minus the derivative of bottom part, just multiply on the upper function. E square r stays the same, and derivative of these brackets will be 2 multiply on the r plus r. That is how we obtain. And divide on square of bottom part. If it was in square and we taking also in square, it will be 4 power of bottom part. Just general formula of derivative of the ratio of complex function. That is why if this derivative should equals 0, then it means that upper part of our equation should equals 0. Here it is. And we just enclose all brackets that we have and grouping all values that we have, as we see these two parts equals and disappears, and we have r load square with plus 2r load square with minus. They also will take in difference, and the result that r square of generator minus r square of load should equals 0. Then the final answer for the 0 derivative for maximum point of power should be condition of equality of these two resistances. If we will take resistance the same as resistance of source, the power will be maximum. It is condition for maximum power. But it has some disadvantage. Why is it so? Because if we return to the graphs, we should take some, what is power generally? Power is I square on this R load. Then power is multiplication of two functions. As power should be bigger, then resistivity of load should be bigger. But if resistivity of load increase, current decrease. That is why we should find some value of resistivity that current stays not very small, but this resistivity also shouldn't be very small, just to obtain some big amount of power. And this condition of maximum power, as we find solution, as we proved, it should be equal of these resistivities. But the main problem that if these two resistivities are equal, then we heating the same time and load and our source energy that takes from the source, it divides on two different parts, and the heating, the positive work, the heating of our consumer equals our negative work, our losses inside system, because also we heat internal resistance. And if we will build such called efficiency curve, coefficient of efficiency as new, it equals positive work into the total work, and because our work or our power is a joule heating, then we could write joule heating using currents, positive joule heating into the total joule heating of the whole system. And we could divide on current as the same function in upper and lower part, and we obtain that efficiency coefficient equals such equation, and it takes in percent. As bigger load, as closer this efficiency coefficient to 100%, because if our load moves to infinity, then this coefficient close to 100%. To 1 or 100%, let it be point here, or our load, no, infinity. It should be somewhere here. Very high amount of resistivity. If opposite situation, the resistivity of load, the consumption, is close to the zero, then the efficient coefficient equals 0, because we have no consumption of energy. All energy that we have moves to heating of our source. And the efficiency curve, it will be as a line, and it could be said that it is efficiency line from 0% to 100%. And the point of maximum power, it will be 50% of efficiency, because we simultaneously heating consumer and source, and this heating is equal. That is why the final conclusion, if we have some informational system with low current, low voltages, and our main goal to transfer some signal with maximum intensity of this signal, and losses is small because currents and voltages are small, and the money question isn't important because value of transporting signals is very small. Current voltages. But if we are speaking about industrial transporting power, not signal, but power, it will be high voltage lines, it will be high current lines with amperes or kiloamperes, with kilowatts, volts or megavolts, and each small difference in value of voltage and current will transform in lots of money that we could or save or spend. That is why for power transmission, we firstly try to reach the highest efficiency coefficients. We are working with high value of resistivity. It will be this part of the, sorry, not here, not this. It will be this part of diagram where power not so high, but the efficiency is very high and losses is very small. We are transporting power more slowly, but all money that we spend is spent on the right thing. The opposite situation, if we are transporting some signal with small currents, small voltages, and only that we are interested in the intensity of signal. That is why we are working in this region. With highest power, okay, 50% of money will be spent just on heating of the source. But the amount of money will be not so important, will be small, because the intensity of signal is small. Small current, small voltages. We are making some signal in milliamperes, in couple of volts, and it doesn't matter, the difference in money will be also very small. If we are transporting power, not information, but power in high voltage line, power systems, then it will be in kiloamperes, it will be in kilo or mega volts, and the differences between these two values will be at least, it is 10 on 6 power, here is 10 on minus 3 power. The difference will be 9 points 10 in 9th power will be difference between these two numbers. That is why that is the main difference between two approaches, what we are mostly interested in. Or we could transform power efficiency, but the amount of power will be small, or we could transfer high amount of power, but with small efficiency. Okay, maybe just to also some, because it is one of the most important ideas. That is why I concentrate such much time on it, and maybe something speak couple of times the same idea. If everything is clear, then sorry for it. Couple words maybe about money. If here in a region of small area of current and voltage, for example, we also spend small money, small amount of money. For example, or we transport with efficiency 50%, and from, for example, $10, $5 we are throwing away, but our positive work also will cost on $5. And for now, it's not so important. Or we spend $10, or we spend $5. If twicely increase in value makes opportunity to obtain the highest amount of signal, then okay, it will be more costly, but we will reach our goal. But if we are working in power engineering, then we are speaking about hundreds, thousands of dollars. It could be, for example, couple thousand of dollars cost of energy consumption, and it is quite important. Or we spend 10,000, or we spend 5,000. And for now, for our goal, then it obviously that it will be much better to transfer power more slowly, but with more efficiency, with lots, with higher, when all our money will be spent on the consumption of our load. That's all. That's all what I want to say about direct current. Is everything okay? Is everything clear?
Okay, clear.
Yeah, perfect. If I repeat something lots of times, then sorry for it, because
No, I think it must be important that you lost you spent lots of time.
Okay, then thank you. Okay, then I think let's have very small break, about 2-3 minutes, just little bit clear our thoughts and transfer on the new material, because now will be completely new mathematics, completely new ideas when we speak about sinusoidal current. Then let's have short break about 2 or 3 minutes. Okay, I think let's continue.
Okay.
Okay, then let's move to the new material. Let's speak about ideal sinusoidal current. Generally, a sinusoidal current is easier to generate because it could be generated using rotational mechanics, and easier to transfer because all transformers they are operating on sinusoidal currents. About generation, the simplest idea how we could obtain alternating current, just making some wire, just one moment. We'll have some statical part of, or I think, just one moment. I think I have picture not to draw it from now. Just one moment. Yeah, sorry, it is on Russian, but I will translate on English. We have some statical part of electrical machine that stays statical. We have some coil as loops of wire, some coil, and this wire is perpendicular to the plane that we see. It goes inside this picture, just perpendicular that we look on it, and it encloses like this. If we will draw other coordinate representation, for example, it is let it be z, let it be x, and we are looking on some cross section of y. Then if we will look on this picture as that y x, or just to draw the point here. The picture will be like that. It will be wire that makes circle. Metal wire. And we are looking on the cross section of one wire. Here it is, this cross section, and cross section of other wire. Here it is. Then if we'll make some rotational magnet inside it, it could be made, for example, just electrical magnet with applying some direct voltage, and we'll rotate it inside this statical point. This rotation will be also here. It will be inside our wire. And depending on the direction of magnetic field, if the direction will be perpendicular to the cross section of our wire, then it will be maximum magnetic field. All magnetic field, we also could draw the projection like this. It is one wire coil, but it could be multi-wire coil. It could be just some multi-wire coil. Then, if magnetic field is perpendicular, then the amount of magnetic field is maximum, and the current and the voltage that generates on this coil became maximum. If we connect this coil to some system, the current will be maximum. If the direction of magnet is opposite, is inside the is perpendicular to our cross section of wire, then voltage became 0 and current became 0 because all magnetic field is generated in perpendicular way and does not move through the cross-section of wire. If once more direction is similar, this situation, then all magnetic field moves through the coil. And that is why the amount of voltage will be maximum. Because we have circular rotation, then all variants of the positions of this magnet and all variants of instantaneous value of voltage and current will be inside points of sinusoidal line. If this movement making whole circle, that this magnetic field also makes whole circle, and from the maximum value of voltage in serial, in parallel way, and minus amplitude from the opposite way, we will obtain 0 points for these positions, of electrical magnet. And all variants of signal that we will obtain will be sinusoidal line. That is why the simplest way for electrical generation is to make rotational machinery and to obtain a sinusoidal curve for generation voltage. That is why it has lots of application. The second reason is efficiency of transportation. Because we have Joule heating, I square R, let's assume that we have some wire, and we want to transport electricity from point A to point B. This wire has some constant resistivity. We cannot influence it because generally we could take some big cross-section. Bigger cross-section will decrease resistivity, but a high cross-section costs high amount of money. That is why the value of cross-section is we cannot take any high value that we want. That is why we have some limits for resistivity of our wire. That is why I'm speaking that it is constant. That is why only difference how high we will heat this wire and which amount of money will be thrown away is what current do we have. In the same way, power equals voltage and current multiplying current. And if we want to transport some constant value of power, then it means that we could change only voltage and current. If we want to transport, for example, 10 kilowatts of power transferred to some point, then we could take or 10 kilovolt voltage on 1 ampere current, or we are taking 1, for example, kilovolt and 10 amperes power. Or let's say in this way, we could take 10 just volts voltage and 1 kiloampere current. The power will be the same. But the main difference that in first case, we are spending 1 ampere on resistivity. For example, resistivity 10 ohms. In first case, we are spending 1 square on 10, just 10 watts power on heating on resistor, throwing this electricity away. In the second variant, we are spending 1000 in square, it is 10.6 on 10 watts of power. Just to heat a wire that we don't want to heat. That is why it is a quite important thing, according to efficiency, that as smaller current we will take, will better for us in terms of efficiency. That is why for taking smaller current, but for reaching the same power, the voltage will be high. That is why we are transporting electricity on high voltage and ultra high voltage. We are starting from, for example, 10 kilovolts and so on for 110, 220, 500 and so on. Value of kilovolts voltage. It is much efficient. But then appears second problem. If we transport power on such high voltage, then when this voltage comes to our house, it should be safely. It should be safely. Then we somehow should decrease this amount of high voltage into general 220 or 230 volts inside our flats without kilo. And for this purpose, it is quite useful things as transformers. Transformers, they are operates on magnetic field. It is generally 2 coils with ferromagnetic core inside. Ferromagnetic is just for concentrating magnetic field, but generally it's just 2 single coils. And by the difference of number of loops will be difference in voltage of first coil and second coil. And it is quite simple way to decrease amount of voltage. For direct current, we cannot do such way because transformer will not operate on the direct current. That is why it is the second reason why sinusoidal current it is so highly used, so widely used in our ordinary life, because it is simple to generate from the rotation and simple to transfer from one point to another, transfer with high voltage, with high efficiency, with small losses, and after it could be also quite simple decreased to, could want to say, to safety values from our ordinary life, but 220 is not so safety, but it is much safer than kilovolts region. But in any case, it could be simple transfer with small losses and simple decreased to more safety values. That is why. That is why we are speaking about sinusoidal current. Oppositely to direct current. Then If it's sinusoidal, from the general physics course, it could be write as sinusoidal function, which has some amplitude, speed of rotation, and initial angle. It looks like here. Let's look on it simultaneously. Here it is. Any value that we speak previously became a sinusoidal function that has amplitude value, maximum value, speed of rotation if we are speaking about electrical magnet and some coil. I try to draw in 3 dimensions. That is why this magnet is perpendicular in perpendicular plane to our coil, to our wire. Then the speed of rotation of this electrical magnet became this omega that makes period of oscillation of sinusoidal function. And initial angle. Sinusoidal function can start not from 0, but from some initial point, could be moved from 0 of the coordinate plane. That is why 3 main characteristics as amplitude, frequency, and initial angle. The same for voltage, the same for electromotive force. And the main problem that all these values will be some sinusoidal functions with different amplitude and different initial angles. Something like that. Just one moment. For example, if we have some circle with sinusoidal electromotive force, we could point some direction on the 0 point of time and drawing the arrow as we draw, but mean that it is sinusoidal source. And 2 elements, let it be some 2 unknown elements. We are not concretizing or it resistor, or it coil, or it capacitor, some elements. 1 and 2. And inside this system flows current. Then, in general form, all our functions, first of all, will be sinusoidal. The second will be moved in some angles between each other. And it will be quite hard to calculate this system. As you see here, for making calculation, we should fix some point of time, for example, for some moment t, calculate points 1, 2, 3, 4 as instantaneous values of this sinusoidal function. But in the next point of time, the values will change. That is why, general, we have to calculate all these sinusoidal functional equations in the form like here, and to obtain them some way. It is the main complexity of sinusoidal current if we want to compare it with direct current. How to find these sinusoids, and all these sinusoidals will be with different angles, with different amplitudes, only frequency will be the same, because we transport electricity on some frequency, but all other values will be different. Then, for this purpose, was made some method how to simplify this calculation. And here is a situation that I drew previously, that voltage and current will have different initial angles. And if we are speaking about some element, one of very important characteristic is called as phase difference angle or phase shift angle. It is point as phi. It could be found as difference of initial angles, voltage minus current, Psi minus Psi. And why this characteristic is important? Because for three main elements, the numbers will be quite concrete and also different. For resistor, the shift angle equals 0. For coil, shift angles equals plus 90. For capacitor, shift angles equals minus 90. And we have a special measurement device that is called phase meter. And this measurement device could measure, it have two pairs of connections. One connection on voltage, one connection on current. And if we can measure phase difference angle, we could identify which element do we have. For example, you have some black box with unknown element, but you are measuring shift angle and obtain 0. You definitely know that inside this black box is a single resistor. That's all. For example, you are measuring shift angle and obtain 90 degrees. Then you know that inside this black box is a coil, definitely coil. For example, you are measuring angle and obtaining 45 degrees. Then it's mean that inside this box, you have resistor and coil. That's all together makes the angle 45 degrees, and so on and so on. We will also check it on practice a little bit later, but the main idea that you have to remember that it is important characteristic, the difference between these two curves. Why these angles appears? Why we speaking about these numbers? Because of main physical equations. For resistor as power consumption, we know that that equation which combines voltage and current is called Ohm law, and it combines these two values by resistivity. Just ordinary Ohm law by the heating of resistor, voltage and current proportionally to resistivity. That is why if we have some curve for voltage, then curve for current should be exactly the same. Maximum under maximum, minimum under minimum. The same extremum points. And it is mean that shift angle equals 0 because initial voltage and current angles should be the same. Then let's move for coil. For coil, from the general physical formula, we know that current appears, if current flow, it generates magnetic field, and voltage from this magnetic field, it appears if magnetic field is variable. Voltage that appears on the coil equals derivative from the current multiply on the characteristic of coil, what type of coil do you have, how it makes magnetic field, how good is for magnetic field, and if, for example, number of wires increase, magnetic field increase, if material is better, then magnetic field increase, and so on and so on. If geometry is better, then magnetic field increase. And all these parameters could be height in one coefficient that is called inductance in Henry, and pointed as L. Generally, in physics, voltage appears from the changes of magnetic field, and it is mean that number of wires multiply on such called flux and magnetic flux and derivative per time. If we will write magnetic flux in the term of current and voltage, it will be inductance and current as a derivative. These two values are equal. That is how we obtain a general equation that voltage is derivative of current and multiply on inductance. Then, if our current is sinusoidal line, for example, current, we point as blue. And it is sinusoidal curve, sinusoidal function. Sorry. Then, derivative from sinusoid gives us cosinus. And cosinus is moved comparably with sinus on 90 degrees. Cosinus, if sinus from 0 equals 0, then cosinus from 0 equals 1. That we have shift angle 90 degrees between these two curves. Because of derivative, we have shift angle. If current is sinus, voltage is cosinus, then this shift angle is positive. From 90 degrees, we take indifference 0 and obtain 90 degrees with plus. That is why I speak about 90 degrees for coil. For capacitor, we obtain exactly the same idea, the same approach. We have capacitor, electric field inside it, two plates of conductor, dielectric medium between them, and electric field in this dielectric medium. Current equals charge multiply on voltage. Sorry, no. I speak about power. Current equals derivative of charge per time, and charge that is stored inside equals capacitance on voltage. And because capacitance, the characteristic of capacitor, how much charge could it stores, then we have derivative from voltage on the capacitance C. That is why for capacitor, the formula is quite similar, but not derivative from current, but derivative from voltage. That is why if we have sinusoidal curve for voltage, then current will be cosinus function and moved on 90 degrees compared with this sinusoidal. Not voltage by current, but current. And the shift angle will be minus 90 degrees. Here we have, for example, 0, 0. Here we have 19, 0. Here we have 0, 90. That is why we obtain minus 90 degrees. If we have combination of elements, then the shift angle will be in limits from plus 90 to minus 90 in some limits. It could be plus 60, minus 45, plus 73, any numbers in these limits, inside these boundaries. And main properties, then, we are speaking that for resistor, the main formula is here. For coil, the main formula is here. For capacitor, the main formula is here. And our next task to find how to deal with this formula, not to calculate the differential equation. Because, for example, if we have source of energy, resistor, coil, and capacitor, and we'll write the Kirchhoff's law for this circle, that electromotive force equals voltage on resistor plus voltage on coil plus voltage on capacitor, and we'll write voltage of coil and voltage of capacitor, we'll obtain a differential equation. And it is not very good idea try to solve the differential equation in such task. We have to simplify it somehow. How it will be next time. Using complex numbers, why do we use them, and how using complex number we could obtain the solution. For these materials, is everything okay about main elements? Is everything clear?
Yeah, clear.
Perfect. Glad to hear it. Then let's see. Let's see what we have about general characteristic, sinusoidal function with main parameters, because instantaneous values in different points of time differs, then we have such called root mean square value, it is energetically or power average. It means on this amount of current on direct current, we will obtain the same power as for our sinusoid as we see it here. Because instantaneous power in each point of time will be different because current in each point differs, but the total power from the period of oscillation will be the same as we take constant value of current of such root mean square value. How it could be proved, we'll speak next time. Let's see what we have for now here. Okay. For now, main elements. Yeah. We discussed the characteristic of main elements, coil and capacitor with, where it's the curve, okay, just comparably characteristic. Here it is. Sinusoidal curves for capacitor, sinusoidal curves for coil, and sinusoidal curves for resistor. For the next time, we will start how to deal with differential equation, how we could not to solve this differential equation, how we could transform sinusoidal function into the complex plane using complex number. For today, I think it's enough. That's all. I think if you have any questions, please welcome. If no, just wishing you a nice day, good luck, and see you next time.
Okay, I don't have a question. Thank you. Have a nice day too. Bye.
Okay, welcome. Have a nice day too. Bye-bye.